Okay, we have indeed, the first speaker has started with some slides, and this is a very important meeting for us at the Science and Engineering Council because the science fair is something that we all support annually. And we're very pleased to be able to have had the science fair this year and to be able to present the award winners. I'm Mary Howe Grant. I'm a former president of the Science and Engineering Council, and I'd like to acknowledge those board members that are here, both in person. I think Yvonne DeGraw and Bill Theringer are on site. Is that true?
Yes, Mary.
And Bob Lilly and Joseph Stronks are in the audience via Zoom. So we'd be pleased to have you talk to any of us. If any of you who are listening would be interested in joining our board, we're in need of a program chair, and we're just in need of board members in general. And I would also like to thank our sponsors for the Science and Engineering Council. They include Community West Bank, where this is being held. And I don't have the list in front of me, I'm sorry, but we'd like to thank them. The Science and Engineering Council also provides a scholarship for STEM students through the Scholarship Foundation of Santa Barbara County. And we, as you know, present meetings on usually on the second Wednesday of each month. With that, I'll turn this over to Yvonne, who will tell you about this year's winners and introduce our speakers.
Okay, thanks, Mary. I'm here in person and just wanted to welcome everybody to our annual meeting where we present our awards for the science fair. So there's a separate organization that does the Santa Barbara Science Fair. They make their awards, but we've also historically had some awards and some professional trophies that you'll see later that we provide as part of our support for that organization. So today we're going to start off with our junior division winners, and they're going to give presentations. Those people are remote, the juniors, and so they'll be sharing their slides, and then they'll give about a 4 or 5 minute presentation of their research, and then accept questions either from Zoom or in person. And just for a few minutes, I've got about 7 minutes scheduled for each, so we'll move through these. Our first award winner is for junior biochemistry, microbiology, and pharmacology, and that's Aryan Naik. And you can correct the pronunciation of your name if you'd like. So go ahead, you can share your slides and go ahead and speak. And unmute yourself.
There you go. And then where I showed you is share that, share the screen too. There you go. And then you should be able to talk.
Wait, just to clarify, y'all can see my screen, right?
Yes, we can see your screen.
Okay, so one day when I was on a family trip to the beach, I had to put sunscreen because it's extremely hot. And mind you, I really despise putting sunscreen because I just think it's tedious, and putting it all over your body numerous times just like wastes a lot of time rather than what you can be doing as playing in the beach. So after coming back from the beach and sitting in the car, I wondered what else could be used other than sunscreen to help protect our skins from this harmful UV radiation. So after doing some research and conversing with my parents, I found out about natural antioxidants. What natural antioxidants are is that they're substances that reduce the oxidative stress from the UV radiation. And oxidative stress is an imbalance created between the production of free radicals and the body's ability to neutralize them. And free radicals are molecules with unpaired electrons. And the free radicals produced by UV radiation are called ROS, which stands for reactive oxygen species. Having an excess amount of these ROS is what causes skin cancer in our body, because these ROS alter the DNA of the cells inside of our skin, which in turn causes skin cancer. This initial research and inspiration resulted in me asking the question, what is the effect of natural antioxidants such as vitamin C, vitamin E, green tea extract, and curcumin, and combinations of all 4 of those antioxidants, a combination of vitamin C and vitamin E, and a combination of green tea extract and curcumin, versus no natural antioxidants used, on preventing the cell damage of Baker yeast cells from UV radiation measured in cell viability percentage. I hypothesized that the combination of all 4 antioxidants would have the highest cell viability percentage, meaning that it would be the most beneficial for protecting your cells from UV radiation. And I hypothesized that because of an effect called the synergistic antioxidant effect. That effect states that when multiple antioxidants are used to help prevent UV radiation from damaging your cells, all of those antioxidants will work together in different areas of your cells inside of your skin, so that it protects more of the UV radiation from damaging your cells. The main materials I used in my experiment were a microscope, all 4 of the antioxidants being green tea extract, curcumin, vitamin C, and vitamin D, a micropipette, a hemocytometer, and cover slips for the hemocytometer, and a UV radiation flashlight to represent the sunlight. To conduct my experiment, I first had to create the initial yeast sample. And to do that, I poured 5 grams of yeast into 100 milliliters of warm water. And the reason the water had to be warm is because that's what allows the yeast to activate, meaning the cells in the yeast become alive. So cells can actually die, or some can stay alive from the UV radiation. After waiting 10 minutes for the yeast to activate, I used a pipette to pour 3 milliliters of this newly created yeast sample into a test tube, and I repeated that step 9 more times so that there's a total of 10 test tubes per control or experimental group in my experiment, and I repeated that process 7 more times so that there's a total of 80 different test tubes with a yeast sample. Now that all of the yeast samples were created, I had to create the natural antioxidants. However, green tea extract and curcumin came in the form of pills, or capsule-like objects. So to access the powder inside of them, I first had to cut those open. I used the total amount of antioxidant of a sum of 0.4 grams so that my results could be constant and all the proportions would be in a certain ratio so that I can compare the results from each different group in my experiment. For the groups with 4 different antioxidants, I would use 0.1 grams of each antioxidant, and for the groups with 2 different antioxidants, I would use 0.2 grams of each antioxidant. Now that I had all of the natural antioxidants created, I had to pour the natural antioxidants inside of the yeast sample so that each yeast sample would have their respective antioxidant. Now that all of the samples in my experiment were created, I had to shine them under a UV lamp for 15 minutes at a height of 5 centimeters, because the UV radiation is what kills the cells inside of the yeast. After that was done, I had to load the hemocytometer, but before that I had to do a trypan blue dye test. Trypan blue is a liquid which has a special property in which cells that are dead absorb the color blue, and cells that are alive stay a whitish or clearish color. The reason I had to do this test is because I can't just guess which cells are alive or dead. I can't say, oh, this cell looks dead and this cell looks alive. I have to know it as a fact, which is why I conducted that test. So after conducting the trypan blue test, I loaded the hemocytometer and put the magnification of my microscope to 2500x so that I could view each cell and count them manually to calculate the cell viability percentages. After I finished all of those trials and recorded all of my results, I graphed them into my and these graphs represent my results. This first graph, where my mouse is on, represents the averages of every single group in my experiment, and it shows that the combination of all 4 antioxidants had the highest cell viability percentage, followed by the rest in this descending order. This graph over here shows every single individual trial in my experiment represented in lines, and it's an easy way for you to see any outliers in my experiment.
Show them how to share screens.
Okay. This graph over here represents the improvement compared to the control group, and the control group in my experiment was the group which consisted of no natural antioxidants, because it's unlikely for humans to use antioxidants. And this group over here shows how consistent every single trial in my experiment was, and is an easier way for you to see outliers from every single group. In conclusion, after conducting the experiment, I found out that my hypothesis was partially supported. Although the combination of all four antioxidants worked the best, I actually hypothesized that the combination of vitamin C and vitamin E would work the third best. However, that actually worked worse than green tea extract and curcumin individually. And the reason is because vitamin C and vitamin E work in the water-soluble parts of the cells, and vitamin E protects the cell membranes of the cells. However, green tea extract and curcumin fight back these ROS that actually harms our cells and it repairs the DNA of the cells. So as a result, they are much better than the combination of vitamin C and vitamin E. My experiment wasn't just to find out which antioxidant was the best. It's also a step closer to preventing skin cancer from occurring in our body, because finding out of this combination of antioxidant and seeing how it actually works better than other antioxidants, or better in protecting your cells, shows that this is just one step that can be used to prevent skin cancer from occurring in your body, because it can be both consumed and placed on your skin just like sunscreen, which is why I did this experiment. However, one improvement I could do to this experiment is actually placing the test samples outside in the real light, exposed to actual sunlight, because that's just a way to represent humans and represent actual sun rather than using a UV lamp. So overall, that was my experiment, and thank you for listening to my presentation.
Thank you. We have time for 1 or 2 questions. Does anybody have a question on Zoom? You can just speak up if you want.
How do you distinguish the use of, say, the green tea extract from using it on the skin or using it at just drinking the green tea extract?
Yeah, so you can, there's actually, I know some sunscreens actually contain green tea extract as one of the ingredients. Like there's green tea extract specialized sunscreens, and you can also have pills. Like as I said in my experiment, my green tea extract was inside of a capsule, so you can drink that pill because it contains the powder inside to strengthen your cells internally, or just drink green tea itself because that also contains a natural antioxidant. But to putting it over your skin, just like sunscreen, I know some sunscreens that I've researched on actually there's like certain sunscreens that just contain green tea plus whatever sunscreen it is, because it's a green tea specialized sunscreen, so that your UV radiation protection is much more increased than rather using singular sunscreen itself.
So these were experiments other people had done that you're talking about, because you didn't do that yourself.
Oh yeah, in my experiment I only used it internally.
Yes.
Yeah.
Okay.
Lynette, you had a question?
Sorry, that was a clap, but yeah, thank you for a really good presentation. I agree with you on, I'd love to see an alternative to wiping on sunscreen all the time. Really good
Yeah.
information.
Yeah.
Thank you. So now we have our next speaker. That's Trolin Tran, who won the division for junior biology and behavioral sciences.
I'm gonna go bring Cholin inside because she's waiting outside the room. So I'll mute for a second.
Yeah, maybe we can have people kind of queued up. Thanks.
Yeah. Okay, thank you.
I'm going to do that, and I'll say that the certificates and the checks for the winners of the junior will be mailed to them. So they'll be receiving that. So we don't have certificates here to present to them over Zoom today. But those will be sent by mail. Okay, great. And let's have Leo queued up for next, okay? Hi, Trolin. Go ahead and unmute.
Where do you stand? You sit on the chair.
Let me, sorry.
Wait,
Hello. Sorry, just gonna help her with her drive. This is yours right here.
Yeah.
Great. Start with your introduction. And then
Wait, Arian, okay, go ahead.
Just click share.
Just hit share.
Good morning. My name is Cholin Tran, and today I'll be presenting a brief walkthrough through my project, Hydrogels, a Transformative Technology of Agriculture. And so I first thought of this idea because I live in California, which is an arid region that is usually known for its rising drought crisis. And I also live with a mother who has a strong devotion to gardening and also harvesting her own crops. But I soon realized that her dedication to nurturing these crops and vegetables required excessive water and time management, which I decided to find a viable solution for and came across hydrogels. Hydrogels are three-dimensional cross-linked polymer chains capable of remarkable fluid retention. My investigation of this project specifically focuses on exploring eco-friendly alternatives to synthetic polymers. I explored different semi-synthetic and polysaccharide-based solutions such as HEC, CMC, and agar, and used that to add to my plants, which I used radish. My question was, what is the effect of different hydrogel solutions, agar, HEC, CMC, HEC and agar, HEC and CMC and agar, versus no hydrogel solutions on the vertical stem growth of radish plants over a consistent growing period of 4 weeks? It was predicted that the various hydrogel solutions would be added to the radish plant plots, then the vertical stem growth of those plants would increase. In this experiment, I used agar-based powder, HEC powder, CMC powder, citric acid, Petri dishes, potting mix, 28 plant pots, early scarlet globe radish seeds, and measuring tape. And as you can see from these pictures, these are the hydrogels that I made in the Petri dishes. In this experiment, I labeled 5 Petri dishes with their name and group numbers. Using a weighing boat and scale, I individually weighed the mass of each polymer and poured 50 milliliters of hot water into a beaker with the combined polymers. I stirred all well until all was dissolved, and I poured the liquid solution into each Petri dish. I placed all the liquid hydrogels onto a counter to set and cool overnight, and once all the hydrogels solidified to a gelatinous consistency over 24 hours, I cut them into cubes and distributed the hydrogels evenly among the 5 radish plant pots per group. I ensured the hydrogel pieces were sitting above the soil to see the effects of how hydrogels they swell over time. I repeated steps 1 through 8 for 5 more groups with 5 trials per group, and watered the control group every 3 days to avoid overwatering. I measured and calculated the average vertical stem growth of each group after a consistent growing period of 4 weeks, and after I recorded all data and results in a logbook. However, after recording my results, my hypothesis was not supported. In contrast to my original predictions, Group 1, agar, had 0 growth at all. However, the group with HEC and agar had the greatest height of 7 centimeters. I would like to add on to my challenges faced that to my outcomes, citric acid had a major effect on plant growth. Citric acid increases acidity, which drastically alters soil pH. Recommended soil pH of radishes are 6 to 7, but however, if the soil is too acidic or alkaline, plants will exhibit nutrient deficiencies or toxicities, which I believe affected my plants the most. Another challenge that I faced was that weather and season also affected the plant growth, because the lack of sunlight and consistently low temperatures could have hindered the nutrient retention and the growth of the plants. Future improvements and research that I could add on to this experiment would be to conduct the trials during the summer for a longer time period to increase reliability and also to optimize nutrient retention and sunlight. However, if I could conduct this in the winter, I could use a full spectrum UV light to stimulate sunlight. But also in the future, I could add less citric acid, measure the amount of water used, use more polysaccharide hydrogels, which are natural hydrogels, and measure soil water retention and photosynthesis rates, and also test different food crops and soil types to see in the perspectives of different farmers. Thank you.
Does anybody have any questions? Anybody from the Zoom? Oh, here, go ahead.
Yes, yes. I'd like to know how one,
You have a question? Caitlin?
I was wondering why the agar and the I think HEC hydrogel worked best for the plants compared to
HEC is a super absorbent polymer, so it can absorb more than regular polymers. I think it can absorb up to 500 times its own dry weight, but agar acts like a base for hydrogels, which I realized later. And so for farmers, I would recommend HEC the most.
Mary, you had a question?
yeah, what are the decay products of the HEC? So if you're using this on your plants, do you have any decay products you have to worry about being in the plant product that you want to eat?
Could you please elaborate more on decay products? I'm not really sure about that.
Well, the HEC, the HEC was hydroethylene, what?
The HEC was hydroxyethyl cellulose.
Okay. So if this breaks down, a decay product is something that breaks down.
Mhm.
If you place this around your plant and part of your powder breaks down, are you going to have any products that are problematic in the plant you're growing? Do you see what I'm saying?
Yeah. I think possibly, but I didn't really research much about the decay products in this experiment.
Okay, I would suggest that perhaps you might want to look into that in a future experiment. Otherwise, I would say this is a very nicely designed experiment. Right? Good work.
So our next speaker is Leo Liu, who won the division for junior engineering. Can we get that set up? And Leo's project is getting to the bottom of it, the effect of different foundations on resistance to superstructure collapse. So we're getting Leo into the room.
I just started calling the other side. Okay, go ahead and grab it, sweet. Where's it? I don't know. Oh, right here. Thank you.
Leo, come on.
We have Leo up next.
Yes, Leo is coming right now.
Thank you.
Go ahead, Leo, go around.
Okay, here Leo, and we're trying to catch up to schedule here, so be sure to be, fairly brief.
I'll try to.
4 or 5 minutes.
Where is your
Thanks.
thing?
It's the one at the bottom. It's the CSEF on with Sunshine.
This one?
Yeah.
Okay. Should be able to share.
Everyone can see the presentation, right?
Yes, we can. Thank you.
So I decided to start my project this year because of how relevant earthquakes are in the areas we live in and many areas across the world. And so I looked into how engineers can try to minimize damage from earthquakes to a building. And one such way is by using the foundation of the building to prevent collapse. So this year I did an experiment on how different types of foundations affect how long a building takes to collapse in an earthquake. I modeled the earthquake with a shake table, and I used skewers and putty to model the buildings. I went through many iterations of my procedures, using sketches to create different designs for the foundations, shake table, and designing the buildings, before finally landing on the one I used for my project. At the time of the writing of my presentation, I had done 6 trials per group for a total of 24 trials. However, I later increased this to 8 trials per group for a total of 32. So I tried 4 types of foundation in my experiment. these being damper-based isolation, bearing-based isolation, raft, and fixed base. And out of these, damper-based isolation performed the best, with an average of 157 seconds before the building fell, and then followed by raft and bearing-based isolation, which had little difference in the data. And then lastly, the control group, which was the fixed-base foundation, performed the most poorly. Now, this could have been for multiple reasons, but I believe that it is because there are three factors that affect how long a building takes to collapse, and these are the resonating frequency, the forces absorbed by the foundation, and the distribution of mass. I believe that the raft foundation was able to do relatively similar to the bearing-based isolation foundation because of the weight at the bottom. This meant that the center of mass of the building and the structure was able to be kept fairly low, and this meant that the building would be more stable under shaking. Another factor is the absorption of lateral forces. For example, the bearing-based isolation and the damper-based isolation foundations have moving parts. This means that friction between the moving parts, as well as deformation in things such as springs, can absorb some of the energy from the shaking before they reach the building, and thus make it less likely to collapse. Lastly, there is resonating frequency, which means that the foundation can change the resonating frequency of the building enough to the point where it is out of the range of the frequency of the shaking of the earthquake. And this also makes it able to move less and thus make it less prone to collapse. I encountered multiple challenges throughout my experiment, one of the biggest of these being how I designed my foundations themselves. I spent a couple weeks actually experimenting with different types of foundations and different materials to make these foundations before I finally landed on the way I did now. One possible improvement to my experiment would be to do more trials, for example 10 trials per group, or to conduct it with higher quality electronics for more consistent results. Further research could include testing different materials such as plastic or metal, or different mechanisms for preventing collapse in an earthquake, such as a counterweight pendulum.
Is that it?
Yes.
Okay. Any questions? Questions for Leo? That was really interesting and looks like good research and good results.
Thank you.
Next,
Okay, Iman,
Mary.
I'd like to ask Leo how he feels about the following. We had our house, which is an old house, is a frame house. Then stucco put on the outside of it, quote unquote earthquake proofed, by having someone crawl under the house and put in stabilization. And then this is done throughout California, actually. And then there is less of you get a rebate on your earthquake insurance. So the question I have for you is, how do you see this as being helpful? Do you think it's appropriate to get a rebate on your earthquake insurance, after having done this? Or do you know anything about this?
So I think the process you're talking about is the seismic retrofitting of crawl space foundations, which is actually fairly common across California, especially because of how earthquake prone California is.
Yes.
And I think it's actually a quite beneficial of a process because it can help to renovate these older foundations to be less prone to damage from earthquakes, especially in these areas that are thus prone to earthquakes. And I think it is beneficial and it is pretty appropriate that you do get a rebate on your earthquake insurance after that process.
Okay, thank you. Thank you. Thank you for thinking about this. And I'm also impressed with your experiment.
Thank you.
Let's see. So our next speaker is Purva Arul Kumar.
I can bring her in right now.
Okay, great. Thank you. Talk is titled, Papula won the category for junior life science.
No, I did it on like a email.
Holy membranes.
Do I need to eject the USB?
You can just pull it out.
It was alright. Doesn't matter too much, I think.
River, which one is yours here?
Like 7. They wanted to give each speaker 7. Like 5 minutes for presentation and 2 for questions. Not really. They asked like one question.
This is why they asked you guys to send it in a video, in a thing, because it's faster.
It's to like
But I don't know yours is.
No. I mean, if you went in person, you would.
Huh?
You would have gotten
They're
a
in Fremont,
trophy.
California, I think, or
But it's
somewhere
not
over
in
there.
person.
Oh, really?
You're also
They're-
supposed to get
they're
practice
working
in
in
CSET.
area.
Like after CSET.
We're not going
I think we will. They might mail
Is
it.
it this
but
one,
We have
Morgan?
to ask.
Yeah.
Trophy, I don't know.
Probably maybe not, because we're going in person.
Okay, there we go.
Okay.
Hello. So this is my project, Holy Membranes. The objective of my project was to discover how different substances affect the permeability of a cell membrane by using gelatin membranes instead. And I used gelatin since it was a protein derived from collagen, and it mimics the nature of cell membranes, so it would be the best simulator. And it was hypothesized that the vinegar would result in the least substance remaining, the baking soda solution would result in the second least, the water would result in the second most, and the rubbing alcohol would result in the most. So my hypothesis was supported eventually, and my experiment was conducted. So I came up with the project when my grandfather was hospitalized, and I overheard a few doctors speaking about how different medications can have different side effects on his cells. So I started wondering how different substances can affect this cell membrane's permeability specifically. So I came up with the experiment. So after doing some research, I simulated a biological membrane by using unflavored gelatin. And then I came up with my research question of what is the effect of 100 ml of vinegar, 100 ml of rubbing alcohol, 100 ml of baking soda solution versus 100 ml of water on the permeability of a gelatin membrane measured in milliliters with a measuring cup after 15 minutes. So I hypothesized that from least to greatest, there would be vinegar, baking soda, water, and rubbing alcohol. My reasoning behind this was that rubbing alcohol dehydrates the gelatin, which would result in more liquid left in the cup, and vinegar and baking soda solution break down the proteins and acetic acid in the gelatin. So my science teacher helped provide guidance on my experiment, and my parents helped me acquire the materials I needed for the experiment. There was a challenge in finding the correct amount of gelatin strips because some gelatin strips were too strong or some were flavored, which would affect the results. My method was to conduct the experiment. I first boiled tap water in a pan and dissolved the gelatin strips in it. Once it fully dissolved, I refrigerated the solution for 3 hours in a glass container. Then I cut the gelatin into equally sized membranes so that they would all have the same number. Then, to prepare the baking soda solution, I dissolved 1 teaspoon of baking soda in 100 ml of water to balance out the baking soda since I could not soak membranes in powder. Then, in each cup, I placed an equally sized membrane after pouring vinegar, rubbing alcohol, the baking soda solution, and water. Then I set a timer for 15 minutes, and after 15 minutes, I took out the membrane and measured how much substance was remaining in each cup. This process was repeated 7 times per substance. My results supported my hypothesis. On average, the vinegar caused the least amount of liquid remaining in the cup, with an average of 88.4 milliliters. The baking soda solution caused the least amount, the second least amount, with 96.6. The water caused the second most, with 101, and that rubbing alcohol caused the most, with 109.6.
So the graph and the table here show my different trials and how each one was resulting, but there were no outliers and all of them came within the same range. One possible improvement to my experiment would be using a temperature-controlled environment because rubbing alcohol evaporates extremely quickly. And another improvement would be increasing the number of trials and extending the soaking time to achieve more accurate results. So further research could include measuring the pH of my substances before and after soaking to explain how the membrane permeability would affect the alkalinity of the substances. The concept of the experiment can be used in real world with medicine delivery systems, and the wound dressings and dialysis membranes also use permeability to control fluid absorption and toxin removal. So studying how different substances affect membrane permeability can help design safer, more effective instruments for the medical field. The objective of my project was to discover how different substances affect the permeability of a membrane. So my hypothesis was supported, and this is because some substances directly alter the protein network of gelatin and cause a change in the permeability. Vinegar broke down the protein structures since it has acetic acid in it, so it allowed the membrane to absorb the most liquid. Neutral or milder solutions like baking soda solution and water don't really change the membrane structure that much, which would be safer in the medical field. And rubbing alcohol dehydrates and tightens the gelatin, which reduced its permeability and made it let out some liquid. So the results show that my milder solutions would be better for permeability and in medical fields. I designed and chose the experimental setup all myself. I did not take help from any other professional, institutional, or academic resources. And these are my references. Thank you.
Thank you so much. Does anybody have questions for Apurva? Either on the Zoom or here? Really interesting research. Thank you. Our next speaker is Arnav Sharma, who won the division for Junior Physical Science and Engineering. And can we get Arnav?
Okay.
Let's see. Arnav's project was the piezoelectric phenomenon of the effect of disc angle on piezoelectric voltage output. We'll get that set up.
No, I think so. Okay, you
Got it? Screen 2. There you go.
Hey, Arnav,
Can you hear
go
me?
ahead. Yep.
okay? So, good morning. My name is Arnav Sharma, and my presentation is on the piezoelectric phenomenon, the effect of disc angle on the piezoelectric voltage output. So, piezoelectricity is the phenomenon in which certain materials convert mechanical stress into electricity. These materials are used in devices like sensors and watches. My project tested how.
Sorry to interrupt you, but this is about the cellulose. This is somebody else's project you're sharing.
Oh, can you see now?
Yes, now we can see it. Thank you.
Okay. So, my project, piezoelectricity is the ability of certain materials to convert mechanical stress into electricity. These materials are used in devices such as sensors and watches. This project tested how the angle of a piezoelectric disc affected the output of voltage it produces when struck, since tile angle impacts how much force becomes usable energy. it was hypothesized that voltage would be highest at 0 degrees and decrease at 15, 30, and 45 degrees. A marble was dropped onto the disc from a fixed height across 100 trials per angle, with voltage recorded each time. Results supported my hypothesis. Average voltage fell from 634 millivolts at 0 degrees to 463 millivolts, 378 millivolts, and 297 millivolts, a 53% decrease. This shows piezoelectric tiles must be level, and tilt can cut energy output by more than half, limiting real-world effectiveness. So, piezoelectricity is a phenomenon in which certain materials convert mechanical stress into electrical energy. And this was first discovered in 1880 by French physicists Pierre and Jacques Curie. In specific crystals and ceramics, like quartz and lead zirconate titanate, pressures can cause a shift in electrical charge, allowing these materials to generate electricity from motion or respond to electrical signals with movement. More recently, engineers have explored using piezoelectric materials to harvest energy from everyday activities like footsteps or vehicle motion by embedding them in floors, sidewalks, and roads. This is significant because it captures energy that would otherwise be wasted, offering a sustainable and efficient approach to generating electricity from the movement of daily life. I hypothesized that the voltage would be highest at 0 degrees and decrease progressively at 15, 30, and 45 degrees, as less of the impact force acts perpendicular to the disk. I became first interested in piezoelectricity after learning how it converts movement into electricity and seeing its use in sensors and energy harvesting floors. I designed this project to test how disk angle affects voltage, and this was inspired by real-world applications like piezoelectric floor tiles. My parents provided guidance and encouragement, helping me gather materials and stay organized. My science teacher, Ms. Rao, offered advice on piezoelectric principles and experimental design, but all measurements, construction, and data collection were done by me. To execute this project, I first identified the positive and negative leads of the 27 millimeter piezoelectric disc and connected it to a circuit with a capacitor and a resistor, with a digital multimeter to measure the voltage. I constructed my apparatus from plywood, brackets, and a tube to guide the marble so it would hit the piezoelectric disc consistently. For each angle, I fully discharged the capacitor before dropping the marble from a fixed height, then recorded the voltage displayed on the multimeter. This process was repeated 100 times per angle to gather sufficient data for analysis. After completing all trials at one angle, I adjust the apparatus to the next angle, and with double-checking alignment to ensure consistency. The recording voltage were then analyzed to determine how disk angle affected voltage output. I collected voltage measurements from 100 marble drops at each angle, for a total of 400 trials. The results showed a clear trend. Average voltage decreased as the angle increased, a 53% reduction overall. A one-way ANOVA confirmed that the differences between the angles were statistically significant, and a Pearson correlation showed a very strong negative relationship between the angle and the voltage. A graph of average voltage versus angle clearly illustrates this trend, showing that even small tilts significantly reduce energy output. The analysis also examined patterns in the consistency and reliability of voltage readings. While the average voltage decreased with increasing angle, the variability between trials was not uniform. The coefficient of variation was slightly higher at intermediate angles, indicating that small misalignments or slight differences in how the marble struck the disc had a greater impact as the surface tilted. This suggests that tilted installations are not only less efficient, but also more sensitive to minor disturbances, which reduces performance in practical applications like energy harvesting floor tiles. Overall, the analysis showed that both the orientation and mechanical context of the disc critically affect energy output, providing insights for optimizing practical energy harvesting devices. The results supported the hypothesis that the voltage decreases as the piezoelectric disc angle increases. Data showed a 53% drop from 0 to 45 degrees, with statistical tests confirming these significant differences, indicating that perpendicular force is key to voltage generation.
These findings are important for applications like energy harvesting floor tiles, showing that even small tilts can reduce output by more than half, and that real-world losses can exceed theoretical predictions. Limitations included slight variations in marble alignment, dismounting, and environmental factors, which have affected individual readings. The cosine model underestimated losses at higher angles, highlighting the role of shear stress and mechanical inefficiencies. For future work, I would use a mechanical drop device for consistent force, a precise angle guide, and a higher resolution multimeter. Further research could test different disc sizes, forces, materials, and environmental conditions to better optimize piezoelectric energy harvesting. I designed and built the experimental setup, including the adjustable angled platform and guided drop system to ensure consistent marble impact. I selected and assembled the piezoelectric circuit, connected the multimeter, and determined the testing procedure. I conducted all 400 trials, recorded the voltage data, and ensured consistency by controlling variables like dop height and alignment. I also performed data analysis, including calculating averages and running statistical tests, and interpreted the results to draw conclusions about how angle affects voltage output. Thank you.
Thank you. Any questions about the piezoelectric effect or the tests? Thank you so much for your presentation. Our next speaker is Iris Peng. Arnav, could you get Iris?
All right.
Great. Iris is the winner of the Junior Physics, Chemistry, and Material Science Division. And our project is eco-friendly solutions for microplastic removal. So very,
Hi, how is everyone? I just had a question. Is it okay if I have Michelle go? We're having technical difficulty with Iris's thumb drive. So I'm trying to see if her mom can send me a file.
Yes, thank you. It's going to have Michelle go now.
Okay.
So I guess I'll introduce Michelle Zhao, is the winner of both the Junior Environmental Science and Toxicology category and also the Best Junior Project. So Michelle's topic is scavenging microplastics. So another microplastics talk. And we'll get that set up. Speak.
Hello everyone, my name is Michelle. As she has introduced me, my project is mostly about microplastics, but that wasn't the main focus of my experiment in general, actually. So my experiment actually investigates a new strategy of removing microplastics by using ferrofluids, which was originally a method, invented by Fionn Ferreira back in 2019. But I actually added some of my own parts to his project. Like I added some economic calculations and also recycled my own ferrofluid. I made my own ferrofluid using my own recipe, which was originally not explored by him. Currently, he is researching in Dublin, and I think he is a very brilliant person. So I am an astronomy enthusiast, and I could go on the NASA website and research about dark matter, antimatter for many days in a row, like 24/7, if my parents don't call me down for dinner or lunch or anything. So then I found out about something called ferrofluid. It was originally like a prototype for rocket fuel. So what is so special about that is it was originally invented by Stephen Propel back in the 20th century. So what I wanted to say is that because it is actually a magnetic fluid, it can stick to the plastic because it is made of oil and hematite, magnetite. So therefore, it is nonpolar. And since most microplastics are nonpolar, nonpolar and nonpolar stick together. So basically, ferrofluid sticks to the plastic, and then the ferrofluid is attracted by neodymium magnet, and it adds to a very easy removal of plastic. So I'll be going down. So my methods for my experiment was pretty easy. Basically, grab some water, put it in a petri dish. Of course, it's measured. And then I would use vegetable oil instead of mineral oil. Mineral oil is often used for displays because it creates those iconic spikes to the ferrofluids that you often see in museums. On the other hand, I use vegetable oil because it was actually biodegradable in the water, so you won't want to trade away microplastic for an oil spill. So that was one of the parts I added to the experiment that made it my own. So what the results showed was pretty understandable. So 5 millimeter obviously removed more than 1 millimeter, or 0 millimeter, which removed nothing. But what really surprised me was that 1 millimeter actually had around a 70% removal efficiency, which is pretty high, I would say so myself. So from this, I could see that ferrofluid can be very cost efficient. Furthermore, because like my experiment only had a budget of like $25 and like a bottle of ferrofluid this small was like $11, I believe. So I had to recycle the ferrofluid again and again to like reuse throughout my 60 trials. So because of this, I was able to weigh the bottle of ferrofluid after and realized that it was recycled about an 80 to 90% efficiency. So that means like it is very economically feasible because the ferrofluid won't get lost after just one use. So my results show that there were no outliers. Everything pretty went up to plan. That means my data was pretty accurate. I think something I would definitely do if I had more budget or for further research, I would definitely say bring this project to the actual oceans. Like, for example, there's large garbage piles between Hawaii and California. I would definitely go there and then test things out. Maybe see if the ferrofluid actually would, like, say, pick up the larger pieces of plastic other than just microplastics. And I didn't use any AI for this work. I did not receive any academic support. Beyond Mr. Fierra's work, I programmed my own economic model. I also wanted to maximize resources by using yellow grease, which is basically leftover cooking oil, usually vegetable oil, and using iron shillings that are left over from steel factories, in which they're going to throw off anyways, which costs about 50 cents per pound, I believe. And then I am currently developing a cheaper form of ferrofluid, as I said before, and then I believe that this experiment can be brought further and then possibly create a new industry, helping us perform better while removing plastics from the ocean. That way we can have an economic incentive, because most of the other experiments are saying that, oh, we can remove plastic using this method, which costs like thousands of dollars per removal. So what I'm saying is that my experiment is very different, because while we're removing plastics, we're creating jobs, we're earning money. And then, as you can see here, based on my program, by recycling about 5 kilograms, I can earn about $11 at a global rate. But in California, it's actually about $10 per kilogram, which is around double the profit. So that would actually be $20 in the California rate. As for my references, I have all the references listed below. And if you guys have any questions, I will be happy to answer.
Any questions? Anybody online on the Zoom? Thank you, Michelle.
Thank you.
Interesting. Can you see if Iris's presentation is ready for us yet?
I'll ask for you. Thank you. Iris, are you ready? Iris, give me that thumb drive. Okay. Do I stop screen share? You just pull it out. Alright.
So the advisor for all of these projects from Challenger School is Kavita Rao, which I think this is Kavita. This you, Kavita?
Huh? My name is Iris Peng.
So I just introduced you, and you can go ahead and share your screen. That's good.
Scroll down, not this side. Go D, and then find your file. Scroll, keep scrolling. This one, yeah. And then you know what to do? Just hit repair.
Iris's project, just to remind people, is eco-friendly solutions for microplastic removal. It's a different one. Both microplastics, so it's just different methods.
Wait, didn't open.
No, go ahead. You can talk.
No, it didn't open it right.
It didn't show it. It's right here. This is not yours.
No, that's not
We can see it.
You can see it? They said
No,
they can see
not
it.
the right
sweetie.
one? Oh, no, this is the previous
Okay.
one. Yeah.
Let me go back in.
Do it this way then.
Oh, this is it. Yes, it. Good.
Yeah?
Yep.
Yes, we see it.
Okay. Okay. Good morning. My name is Iris Peng, and my project is about eco-friendly solutions for microplastic removal. So, I found through my research that there are these microplastics which can actually cause major health concerns, and studies have found that there have been causes such as Alzheimer's and damage to the vital organs. Now, traditionally, ferric chloride has been used to remove contaminants in general and water and have been found to be able to remove microplastics too. However, it has many disadvantages, such as the cost and also the harm to the environment. Thus, I wanted to find plant-based solutions, and in my experiment, I used okra extract and fenugreek seed powder to test them along ferric chloride to see how they would compare. I also tested different concentrations, 5 milligrams, 25 milligrams, and 125 milligrams. And I put them all under the same conditions using a jar test, using coagulation, flocculation, and sedimentation to remove the microplastics. I hypothesized that 25 milligrams of fenugreek seed powder would achieve the highest removal percentage, since the longer the length of the molecular structure, the better ability to remove these microplastics using a net sweeping effect, and also so that the microplastics can sink down through sedimentation. However, too little of a coagulant will not be enough to cause efficient collision, so I used the median concentration, 25 milligrams, since too much of the coagulant can actually break the bonds through charge repulsion. In my process, I use a 3-step process of coagulation, flocculation, and sedimentation, where coagulation is the process when the coagulants are rapidly mixed with the microplastics in order to remove the negative charge of the plastics. And then next is flocculation, where these microflocks, which are formed from coagulation, can form larger flocks when the coagulants are slowly mixed with the microplastics. Lastly is sedimentation, where these flocks are not heavy enough to sink down and be removed. Now, for my experiment, I had to grind a PV sheet into microplastics, and then I mixed it with water to imitate the microplastics in water found naturally. And then I mixed rapidly at 170 RPM, and then reduced it to 60 RPM each for the coagulation and flocculation process. Oops. Then I let it sediment for 1 hour. I decanted the top portion, leaving 1 centimeter, which I consider the sediment. I mixed in vinegar to break up the bonds and poured it through a coffee filter in order to remove the microplastics and separate it fully. Then I weighed the remaining microplastics and used the formula mass of sedimented microplastics over mass of original microplastics times 100% to calculate the removal percentage. Then I repeated for all of the variables, which I used in 5 trials, and repeated separate trials for microscopic observation of the sediment to actually see the bonds formed between the microplastics and coagulant. Now, I concluded that 125 milligrams of fenugreek seed powder consistently performed the best, achieving a high of about 78%. A trend, and here you can see that trend of 25 milligrams, 5 milligrams, and 125 milligrams from highest to lowest could be seen in ferric chloride and okra extract. However, fenugreek seed extract had a trend of 125 milligrams being the highest. Since ferric chloride and okra extract could be seen to be quite similar, I conducted a statistics test where I could see that ferric chloride and okra were not actually statistically different using p-value t-test. However, fenugreek seed extract powder is definitely statistically different from okra and ferric chloride. I took some pictures of these samples, and you can actually see the plastic sedimented compared to the control. And these are the microscopic images that I took. The control had no bonding. However, in ferric chloride, it was more of a 2D planar structure, while PVC and okra extract had a loose, spongy structure, while fenugreek had a much tighter and denser network. And these are all 25 milligrams for each of the coagulants. So my hypothesis was supported that fenugreek seed powder performed the best, even though 125 milligrams also performed the best for fenugreek seed powder. The high viscosity property and high likely allowed it to the coagulant and microplastics to move together slower, and the high molecular weight allowed it to sink down some of the microplastics. Because actually, I could see for okra extract, some of the microplastics were coagulated but stayed at the top. And long chain structures in the molecular structures in the coagulants allowed for better particle collision and attachment. 125 milligrams of fenugreek seed powder likely performed best due to it not reaching the optimal concentration yet. The most challenging part was definitely the preliminary trials when I tested a lot of different coagulants and microplastics. Since some coagulants didn't fit the requirements I wanted, such as alum and chutazine requiring a pH adjustment in order for it to actually work. And I concluded that would have too many variables in order to be added to my experiment. And also for some of the microplastics, like the polystyrene balls for stuffed animals, they contain too much air and would float no matter what happened. Further research could include using a paddle stirrer and adjusting different pHs, and also testing alum and chutazine and adding that variable of pH to test whether fenugreek seed powder and okra extract would also change. And also testing a narrower range of coagulants to see what ratio of microplastics to coagulants would be the best. Thank you. And if you'd like to see the structures, you can actually see the structures of the coagulants here, where fenugreek had a much more stable structure compared to okra extract, which had longer chains, but probably not as stable in order for connecting to the microplastics. And ferric chloride is an inorganic salt and did not have those branching properties. Any questions?
Thanks. I did want to ask it. I think your last slide kind of answers this, but what is different about fenugreek? You know, because it's an herb that I've heard that it's not safe for pregnant women to take, and has a few other kind of side effects. But was wondering why people have come up with that as a coagulant.
Oh, I've actually never heard of that effect, but yeah, fenugreek is I'm pretty sure it's like very easily found, but these are actually the structures of the polysaccharides, of the main polysaccharides in fenugreek and okra. So also one thing I would like to test is if I could, like possibly removing these specific polysaccharides from the fenugreek and okra to see whether that would actually work better too. Since there are other polysaccharides that might interfere with the process of the coagulation and flocculation.
Any other questions from the room or on Zoom? Thank you so much for your presentation. Could you get your advisor here? We wanted to thank her also.
Oh yeah, my science teacher or yes.
Kavita Rao listed.
Okay, yeah, I'll see if she's. I'm actually not sure if she's available right now. She might be teaching a class, but I can ask. Thank you.
You.
They want to say
Sorry. Of course. I'll switch her right now.
You want to go ahead and start setting up? I don't know how long we'll give this. While we're waiting, I'll just introduce our next speaker, who will be Sungyu Kim Young. Sungyu Kim Young? Kim Young. From Dos Pueblos. Her mentor is Emily Gamil, and her project is the development of an automated engulfment counter reveals efficiency of genetically engineered macrophages in killing cancer cells. Singyu, yeah, is the winner of the Julian Knott Award. And I just wanted to say a little bit about Julian Knott. Julian Knott was a member of the Science and Engineering Council. He was a world record holding balloonist, and he passed away in a ballooning accident several years ago, but his widow has made this award possible just to honor his thing. The idea of the award is to recognize projects that are a little bit out of the box. So not.
Hi, good afternoon. I am Mrs. Rao. I am the middle school science teacher here.
Just wanted to thank you for your work as mentoring the students and bringing them to the science fair.
Thank you so much. It's mostly their effort. I just provide a little bit of guidance, but I would, on behalf of all my students, thank you all too for giving them this opportunity today and always encouraging them to do better and better. Thank you so much.
Great, thank you so much. And we'll be sending certificates for them in the mail and the awards.
Okay, thank you so much. We appreciate all your efforts, and I know you guys organized it so well. My students were so excited. We are looking forward to more opportunities in the future. Thank you so much.
Okay, thank you. Great. So now we have our next talk. So go ahead and take it away.
Thank you. Bye-bye.
My name is Sungyu Kim Jun. So my project was mostly based on macrophages and their ability to engulf many things, but specifically cancer cells. Macrophages are very well known for eating a lot of things, as shown in this, where a macrophage would first recognize a foreign substance or a harmful substance and then form a cup around it before fully engulfing the target and degrading it within the cell. This is made possible by a protein called the RAC GTPase, which in a normal cell is in an active-inactive cycle. So when it's enhanced or always active, the RAC GTPase would do these sorts of things much more quickly and much more aggressively. So with this information, I wanted to see if I could answer two questions. And the first one was, can we build a tool to automate the quantification of macrophage engulfment? And the other was, can this tool be used to replicate results that increased RAC activity can induce more eating of target cells? As you can see, these are not very experimental questions. These are project questions. And so that's what my project was about. The images the cells that were imaged for this project were derived from the femurs of mice with the desired genotype, either hyperactivated RAC or normal RAC. And then time-lapse images were taken using multicolor confocal microscopy over the course of several hours, which each image being taken at 5 to 10 minute intervals. So the biggest part of my project is right in this column here. And basically what I did was I made a cell tracker that could segment that can track the position and location of cells over time. And for this, I first needed to know the orientation, position, and shape of these cells. I did this using a public platform called CellPose, which reads in a given image and basically turns each cell into a pseudo-binary mask, basically labeling each pixel that belongs to a cell with a unique ID number. And after I had those masks, I made a custom cell tracker that can be described with this concept image. So basically, you would have like the shape, an arbitrary shape of the first mask, which we could call that mask 1 at a certain time point, and at in the next time point, it could be when they're overlaid on top of each other, you could see that there could be multiple masks overlapping with it, or just one. It could be several. As you can see in this image, mask number 2 overlaps with the mask in the previous frame much more than mask 3. This one right here, and so it's more likely to belong to the same cell. Another requirement I made just to make sure that cells that were jumping around very quickly wouldn't be assigned to the wrong cell was a thresholding factor, which is basically if the amount of overlap does not exceed a certain amount, in this case 40%, it would not count as the same cell. So in this result, we can see that mask 1 was mapped as the same cell as mask 2, but not mask 3. And so this is an example of the tracking that I did. This is the original image with macrophages in blue and targets in pink. After passing it through CellPose and converting them into masks, you can see that each cell was marked in a different masks, and these colors were randomized to show like that CellPose is only taking one frame at a time. After that, I ran it through a tracker, through my custom tracker, and if you look at this blue one right here, you can watch the blue target. It has sensed a target right here, and engulfs it pretty quickly in about 10 minutes. 20 minutes. And after several hours, the target has been fully degraded, and that's just one example. It's important to note that this tracker is only consistently accurate for short-term tracking, as there are many errors in both my algorithm and the segmentation from CellPose itself. So the tracker isn't very accurate in long-term distances. Later, I do want to make sure that it can work better. And that is one challenge I came across. I found that CellPose doesn't really like to segment macrophages as well as I would like. And because my tracker is not exactly the best, the results in the final column, the results in the final column are mostly validations of information that I already had. So the first one here is I'm comparing counts from CellPose segmentation to counts made manually by researchers where I got these images from, and that would be, and I found that while CellPose consistently overcounts the number of cells in a given frame, it also has a very consistent overshoot, and its overcount is very closely correlated to the manual counts. And the second one is basically the proportion of targets inside of a given time lapse that have been engulfed by a macrophage in different conditions, basically the wild type and the RAC enhanced type. The reason I did this is because the most prominent error in CellPose's segmentations is that when a macrophage engulfs multiple targets, they tend to cut that macrophage up into multiple macrophages instead, while macrophages that haven't engulfed anything or have only just engulfed one target remain just one cell. So when we count targets instead, we can test like the proportion of targets that were eaten in the presence of certain types of macrophages. And you can see that the blue line, which represents RAC enhanced macrophages, and the red line, which represents wild type macrophages, you can see that the proportion of targets engulfed in the presence of RAC enhanced macrophages gradually increases over time compared to when they're in the presence of wild type macrophages, which suggests a higher efficiency rate with RAC enhanced macrophages. This and the final result here is that we found that fewer RAC enhanced macrophages do not eat over time. We quantified the number of RAC enhanced macrophages that remain inactive or that do not eat, engulf any targets. And that's because if there are less macrophages in total that do not become active, then that means it's likely that a larger number are in fact active. So when we counted these, we found that RAC enhanced macrophages tend to have a lower rate of inactive macrophages over time, while wild type macrophages tend to have a more consistent rate, and the difference does remain consistently wide enough to be considered significant, and so that also suggests that RAC enhanced macrophages are more efficient at engulfing and killing targets. So in conclusion, the biggest part of this project was the tracker, and I would have loved to have results for this, but due to time constraints and difficulties with cell post segmentations. I wasn't able to get it very far after this part, that I explained. For future directions, I want to develop like a user-friendly graphic user interface, so that this tool is more accessible for other people, especially researchers. And algorithmically, I do also want to expand this from just 2D images to 3-dimensional images as well, which would be tracking them in 4D, which is 3 dimensions plus time. I got a lot of help from my dad in terms of advice, and from my mentor Emily Gemmel for directions and pacing, and I would also really like to thank the owner of the lab, the one who runs the lab that made these images. Her name is Dr. Denise Montel, and she was very kind to let me obtain these images for this project.
Do we have any questions? Questions from the Zoom? Denise looks familiar. I think we had her as past speaker for the Science and Engineering Council. Let's see, I wanted to present you with your certificate. So congratulations.
Thank you so much.
Thank you. Okay, great. Caitlin is our next presenter. Do you want to come forward and set things up? Caitlin Caitlin Dye is from Kate School. She's the winner of the Best Senior Project. And that her topic is designing a, we're gonna have to pronounce that for the guanidine. Linked protein for targeted degradation of androgen receptor prostate cancer. Something that we can hang that from. It's like the senior projects are moving more to these printed things. So yes, not the trifle selected. I mean, I got that. That's what I'm holding. Actually, can we move it? Maybe over so it's visible on the Zoom and zoom in. But
you think there's like a clip we can use to clip it on the easel?
Don't know. We don't have a clip, do we?
I can hold it from here. So wait, Miss Lord,
I'm totally good. Okay,
wait, Miss Lord. Do you want to hold it from the side?
Feel free to lower your arms every now and then.
Okay, I'm so sorry. Okay. Hi everyone. I'm Caitlin Dye. I'm a junior at Kate School, and my project is basically investigating the linker design principles in PROTACs, which influence the ternary complex stability in prostate cancer. So, yeah, of course. So prostate cancer is a common male malignancy, and basically prostate cancer is driven by the androgen receptor, which is a protein that helps support the DNA replication in prostate cancer cells. And traditional treatments include inhibiting these androgen receptors from helping these prostate cancers replicate within the human body, because the way these androgen receptors work is that certain hormones such as testosterone and DHT, they bind to the androgen receptor, and then once the androgen receptor is activated, then that would cause the DNA within the prostate cancer cells to replicate. So traditional inhibitors try to block these androgen receptors and certain other researchers have designed inhibitors that block these androgen receptors. However, my research expands on the work of PROTACs. PROTACs are basically molecules that, instead of just merely inhibiting these androgen receptors, they degrade the whole androgen receptor altogether. So this prevents resistance from developing within the androgen receptor, so it can help degrade these proteins more effectively. So the way these PROTACs works is they're composed of 3 parts, similar to this chimera over here. The C in the PROTAC actually stands for chimera. It's consisted of 3 parts. And as you can see in my PROTAC designs below, the pink part is the protein warhead. So basically that means that that part of the molecule attracts the androgen receptor. The blue part is the linker, and that basically just connects these pink and red parts together. And the red part is the CRBN ligand. And the CRBN ligand recruits the E3 ligase, which is another protein found within our bodies. So once you have this ternary complex over here, you have the E3 ligase, you have the PROTAC, you have the androgen receptor, then the E3 ligase can tag the androgen receptor and mark it for degradation for the human body. So that is essentially how the PROTAC works. So my research question focused on altering the certain properties of the linkers within the PROTACs and seeing how linker length and linker orientation affected the ternary complex stability. As you can see there in figure 2, here's the ternary complex, and also the binding strength of the PROTAC itself. So to investigate this question, I first designed 6 designs down here. So designs 1 to 3 focused on altering the linker length of the PROTAC. I basically just added more methyl groups over here to the linkers over here. And to talk a bit more about the linker design in my PROTACs, basically I added a biguanide into the linker because biguanides are also shown to have anti-cancer effects. So in creating this type of PROTAC, I was thinking to create like a dual action therapy that can help combat prostate cancer and be more effective compared to other PROTACs that are commonly seen in previous literature. And then designs 4 to 6 are basically the same as designs 1 to 3, except the orientation of the CRBN ligand is different. It's positioned at I believe it's the 3 position of the CRBN ligand rather than the 4 position over here, which is like diagonal versus vertical. So once I've had all of these 6 designs, I used IntelliFold, which is this protein predicting AI software, and I ran these 6 designs and I docked them basically to the E3 ligase and the androgen receptor, and I chose the best model in order to run for molecular dynamic simulations. And the molecular dynamic simulations, the metrics I used for those were ligand RMSD, protein RMSD, and also binding strength. So RMSD stands for root mean square deviation, and that basically measures the average deviation of how much the ligand or the protein moves throughout the simulation compared to the initial conformation or the initial positioning of the ternary complex. So as you can see, the ligand within all of the 6 models remained pretty stable. They had very little variation. It ranged from 0.1 to 0.3 nanometers, and throughout the time, throughout the 1000, throughout the whole nanosecond, throughout like the whole frame of throughout the whole like length of the simulation, it just remained pretty constant. Like all of the ligands, they remain associated with a ternary complex. However, things start to change once you start considering the protein RMSD of all of these complexes. So as you can see, designs 3 and 5 had the least variation, since the arrow bars in these graphs, they represent the standard deviation of these protein RMSD for all of the 6 designs. And as you can see, 3 and 5 remain the most stable, even designs 1, 2, and 6 both had 1, 2, 6, 4. 1, 2, 4, and 6 both had a very high variation due to the larger standard deviation bars compared to the other designs. And as you can see also in binding strength, you can see that protein RMSD stability correlated with the binding strength of the ligand within the ternary complexes. Since designs 3 and 5, they're both relatively very stable. They also both had the greatest binding strength compared to the other molecules. And finally, as you can see in these 2 figures below, basically these are the protein ligand interactions between the ligand and the protein. And here is design 3, and here is design 5. And one reason why I believe that design 5 performed better compared to design 3 was because I believe that linker orientation plays a more crucial role in determining the ternary complex stability and also the ligand binding strength, since it formed more favorable interactions within the ternary complex. So it's not really, you can't really see it that well, but basically in design 3, in both designs, they formed really stable interactions for the CRBN, which is this red part, the CRBN ligand. However, design 3, they didn't really form a lot of interactions with the androgen receptor compared to design 5, which formed an interaction with the linker portion of the biguanide and also an interaction with the protein warhead. So I believe that's why that's why design 5 performed better because of its orientation, because it was positioned, because the CRBN ligand was positioned vertically. So that's why it was more stable, and that's why the ligand binded more strongly within the complex. So in conclusion, I found that linker geometry, specifically orientation, was a key role in determining PROTAC performance. And my future work includes actually synthesizing the lead compound, which is design 5, and experimentally testing it in vitro in order to test its androgen receptor degradation ability. Thank you.
Great. Thank you. Questions from the Zoom room or here in person?
Does RMSD stand for again?
Oh, RMSD stands for root mean square deviation. Basically, it's a measure of the average deviation of the ligand or the protein compared to the initial positioning of the ternary complex.
Okay.
Yeah.
You wanted to present you with a certificate of appreciation, and also notice that there's a check on the back of the of the folder there. So congratulations.
Thank you so much.
Yeah. And we have something for Kate School to display for you to present to Kate School. This is a perpetual trophy. Has your name engraved in Kate School down here.
Thank you so much.
And so it's for the school to display for the coming year.
Thank you.
Okay, thank you.
So much.
Okay. Our next speaker. See, does that stand by itself?
Yeah.
Okay. Great. And you move it over a little bit this way so it shows up on the Zoom. Thanks.
Thank you.
Okay, so first I want to thank for this opportunity, and my project is basically about a portable nucleic acid testing device for primary healthcare settings like homes, schools, and my goal was to develop such a device for those settings, especially in remote areas and rural areas in developing countries. And the reason why I emerged this inspiration was that respiratory infection diseases like influenza, also including COVID, remain as a major threat globally, causing 2 million deaths annually. And they usually have non-specific symptoms like fever, cough. So it's really hard to differentiate different pathogens. However, doctors need to know the specific pathogen the patient is infected to design a treatment for them. And treatment strategies always differ by the different pathogens, like antiviral drugs for influenza A and influenza B, while antibiotics for Mycoplasma pneumoniae, which is a bacteria. So I first researched some limitations of current diagnostic approaches. Commonly used one is antigen-based detection. It's really rapid and it allows self-diagnosis, but it's known for its high false negative rate, and it has a really low sensitivity. And it's not suitable for early stage diagnosis either, when the viral load is pretty low. And on the contrary, we had two different methods, which are real-time qPCR and multiplex PCR. There are traditional methods we use in laboratories and hospitals. They're highly sensitive and highly specific, but they need for trained personnel, and they're highly expensive, and they also require centralized laboratories. So we cannot use them in primary healthcare settings. And these constraints hinder all of those methods used in resource limited settings and point of care testing. So I emerged this idea to use CRISPR-based isothermal amplification, just because this method does not require some strict requirements like the traditional PCR methods, and thus they are really suitable for point of care testing. And there are also some existing CRISPR-based detection technologies like the famous Charlotte-2 platform, but they're also expensive and giant and required centralized laboratories and trained personnel, so they are not suitable for primary care healthcare settings either. So my goal shifted to simplify the process of CRISPR-based detection and to incorporate all of those advantages in a smaller platform. I had four main sections in my methods. First, I designed the exterior and interior structure of my device, which I'll talk about later. In section 2, I designed the biological procedure of my device. I designed the primers and plasmids. First, the primers were for RPA amplification reaction, and the plasmids were used to replace real viruses in my validation and optimization tests. And this is my biological procedure, which is really simple. There are 3 parts. The first part is an RPA pre-amplification at 42 degrees Celsius for 6 minutes to allow the amplification of viruses DNA. And then there's a quick centrifugation by the brushless motor, and then another 6 minutes of incubation at 40 degrees for CRISPR-Cas12 reaction to cleave the fluorescence reporters and allow the optical diagnosis. And in section 3, I optimized my device critical parameters. The first one was RPA amplification time. I tested different times from 1 to 12 minutes and using different plasmid concentrations. Then I also optimized different reagent ratios and 5 different releasing reagents from 1 to 5 minutes. In section 4, I validated my device with 15 real clinical swamp samples I purchased from a hospital, and I compare my results with the standard traditional qPCR method to get a result of my performance of my device. And the first part of my results was my device. I actually brought it here today, and yeah, it's right here. It's really small and portable. There are 3 main parts I included in my device. The first part is a heating unit, which is basically a 40-volt heating pad powered by the power bank right here, and it directly connects to the STEM32 the chip on the PCB board. And the second part is the centrifuge part, which is basically a brushless motor. And the third part is an optical analysis part. I have several filters on the top of my device to transform the wavelengths to the wavelengths I desired for fine fluorescence. And I also use this smartphone as a part of my device to capture the image of fluorescence and as well as connect to my device through Bluetooth to set parameters before the testing procedure. And the second part of my result was some optimization test. I did, like, as I said, different time of RPA pre-application. As you can see in figure ABC, I had 12 minutes, 4 minutes, and 3 minutes. And I got the most intense fluorescence signal in 12 minutes group. But to balance the efficiency and duration of my device, I chose 6 minutes CRISPR plus 6 minutes RPA at the end. And then I also optimize my like different releasing reagent to sample ratios. I got 1:5 reagent to sample ratio to be optimal. And I also tested different lysis time. I got 1 minute to be enough for my RPA reaction. In part 3, I tested my device, part 4 actually, I tested my device with 15 real clinical samples. I achieved a limit of detection, which is LOD of 1 copy per microliter. As you can see in figure, this is 4A. And compared to the LOD of traditional qPCR method, which is 0.5 copy per microliter, 1 copy per microliter is slightly lower, but it's sufficient for early stage diagnosis. And I also, my device also demonstrated 100% specificity compared to other pathogens with no cross reactivity with other viruses or bacteria. In part 5, I tested my device with 15 real clinical samples, and all of them match with the traditional qPCR methods. Move on to discussion part. My device resolves some existing problems of nucleic acid detection devices like long detection time and accuracy, and the cost and requirement of trained personnel and centralized laboratory. My device is really portable and suitable for primary healthcare settings. The app was designed for untrained users like you and me, and the data readout was either positive or negative, which is pretty straightforward. And the performance LOD was 1 copy per microliter, comparable to qPCR. And I also validated it with real clinical samples. Move on to future work. My device can collaborate with an medical Internet of Things enabled system to upload our healthcare data to a cloud server, and the cloud server can upload those data to an organization like the CDC for regional epidemic monitoring or like healthcare monitoring. And compared to other platforms, my device has a faster speed, comparable sensitivity, and because we can just change the parameters of the RPA reaction, 3 targets of my device are also customizable. And the sample preparation step is really simple, which is basically adding the lysis reagent to the tubes. And the cost is like about $10 per test, which is significantly lower than like other traditional platforms. And it's really portable. It's powered by a USB-C power bank, so it doesn't require any AC means or outlets. Thank you.
Great, thank you. Mr. Lacy? Okay. Wonderful, good work. How was the state science fair?
It was pretty good.
So I wanted to present that to you. You're the winner of the Best in Fair, which is a sweepstakes award presented by them. So congratulations on that. And then there's this large trophy. So I hope you have room in your car. And this will also go to Kate for the next year.
Thank you.
Great. Congratulations.
Thank you so much.
So, students, and thank you for all your great work. And good luck in the future as for the senior hires. Have you decided have you thought about college, or I don't know whether you're seniors or juniors or both juniors. You're both juniors, so next year you'll be applying to colleges. Great. Well, good luck with your futures. Thank you. So thank you so much.